Our next speaker is Tim Cat. Tim Cat is an independent software developer and teacher. He's the owner of Wildtree Tech, and he holds a PhD in experimental particle physics. He has worked in CERN and EPFL for several years, and during this workshop he will introduce us to the Binder project.
Yeah. Hi, so my name is Tim, and we will talk about tools for reproducible science, and that is simultaneously something we could do in 2 minutes, or something we could spend weeks talking about. So I tried to make maybe something closer to the 2-minute version, but for the rest of the afternoon. So there will be quite a few things which are, I think, you have to excuse they're like a toy problem or very, very simple, and imagine, you replace it with your complicated research code instead of 5 lines of Python to make a nice plot, and then we say, no, this is my PhD dissertation here. But it gets everybody going, and it means we don't get lost in Python land about this. So the plan for this afternoon is I will show you a few slides just to show you what I think the world should look like. And then I will explain to you all the tools that go into making something that will look like what I will show you. It's super nice outside, so I'm super happy that you're still inside with me. We will take a break, maybe at 3, maybe in 30 minutes from now. And then you can go outside and have an ice cream, or if you're really quick, jump in the lake and then come back. And then we come back. The notes I've written should hopefully have complete sentences in them, so there's not that many slides. So you can go and look at them later on and follow them at your own pace. So we don't have to complete everything there. For me, the best workshop would be if we completely go off-piste and answer all the individual questions you have and help you do what you want to do. The problem is there's probably 30 of you and only 1 of me. So we have to be a little bit more structured there than if there was less of you. So we will try and follow the notes and answer questions as they come up. And if we don't do all the things or skip some of the things, that's completely fine with me. I will ask you if you want to spend more time on something or if you want to move on. And the things that interest you, maybe you can do a little bit more on, and the things that don't interest you so much, then you have a little break. Okay. So if you talk about reproducible science, especially with computers involved, then the question comes up, why, what do we actually need to share with the world, or why would you want to share the software? And is sharing the software enough? Do you need to share even more? And for me, the answer is clear. You need to share the software and the environment in which to execute that software. Otherwise, you're stuck. And the example I use is, in physics, we have a language that we use to talk to each other. It's called maths. And this is the precise expression of physical laws, or laws of nature. If now imagine we hadn't yet invented maths. So we would use words to talk about physical laws. And then Newton's law would look something like this. That is taken from Wikipedia. It's a textual description. And there's several problems with it, I would say. It's quite long, number 1. And number 2, it's not that precise. If you're a physicist, you probably have questions. What exactly did I mean with various things here? And as a physicist, I don't really understand. I have to read this a few times before I really understand what this is going on about. So I would say this is like when you write a paper about something you did with software. You're writing a imprecise version of what you actually did. So luckily in physics we have maths, so we can write Newton's third law, and it's much shorter, it's much more precise, and if you are practiced in maths, it's very clear to you what this means. No, we don't need to discuss for 5 minutes what exactly did you mean with blah blah blah. And so the same is, if you ask me, is true for using software to do research. And then there's a fantastic article in the Atlantic where they say, I think, the journal, or the classical journal paper is obsolete or something like that. So for me the question is then, is paper obsolete? So paper is in the thing you print words on. And it's not completely clear to me that this is true, because we have been using paper in some form or another for thousands of years for communicating information and knowledge to other people. Or maybe it was papyrus, however you say that in English, and clay tablets before that, but in some form it was still paper. And when I say going beyond paper, I don't mean PDFs, because PDFs is, PDF to paper is like paper to clay tablet. It's essentially the same medium. And in this case, this is a PDF of a machine learning paper that some guys, I think, at MIT wrote. And what it is about is not so important for what I will show you. The interesting thing is, it takes a picture, it takes a question written as text, and then it tries to give you an answer to your question that you had about the picture. If you're a modern citizen, then maybe you're interested in machine learning because it's a hot topic right now. Or maybe you're a researcher in AI, then you're interested in this, and you would like to reproduce or get a better feeling for what the heck is going on here, because just looking at the text and just looking at the pictures doesn't tell you everything there is to know about this paper. So what do you need? Well, you need the code to run this, and luckily these guys are super nice. They put all their code on GitHub. So in principle, we have everything we need, no? We can now go and download this and run it. So now the question for you is, how long do you think it would take you to get this running and reproduce one of the figures? And we can have a vote. I will start the bidding at 5 days. Who thinks it will take 5 days?
On a local computer.
On your computer, yeah. You're allowed to email the authors. Yeah, that's also fine. They're very nice. Yeah. So who thinks it will take 1 day? 4 hours, so 1 afternoon? Never? Or I don't want to even guess. No, anybody who doesn't even want to. Okay. So you can see lots of you either don't even want to commit to a specific number, or it is a big number that you're offering. And potentially you've already realized this is like when you come to a magic show and the magician asks you, do you believe I can levitate this pig here? And you're like, no way this is going to work. But you already know that they are, they're going to do it. So I'm going to tell you that this takes maybe 30 seconds to reproduce. And how do you do this? There's a fantastic tool called Binder, which I work on. And there's a public running instance of it called mybinder.org. And it lets you launch code that other people have written and put on places like GitHub in the cloud. And all you need is a browser. And then you can see in a lot of repositories there's a big button that looks like this. Usually it's not quite this big. And all you have to do is click it. So I will do that. So it takes you to this website. And now comes the point of how confident am I in my own work of running this infrastructure. Because what's happening while we're waiting is it clones the repository to some machine in Google Cloud land, builds a Docker container from it, and then launches it. And this can take between 10 seconds and several minutes, or even hours, building the Docker container. And then you stare at this for quite a while. Depending on how popular MyBinder is, just launching it. So in this case, I practiced before. I built this several times, so I knew the build would not fail. So this is why it says found build image and launching it, and now we're waiting for the server actually to spin up.
I have 2 questions at this stage.
Yes.
Does it matter what's your internet connection at all?
No. So, I mean, all you need is a browser that can talk. If you can browse Facebook, this is going to work.
Okay. And the second question is, does it remember that you've run this binder or this repo in the past and reuse anything that has been done, or it really does it from scratch every time?
So
if I close the window and I do it again in 10 minutes, will it just rebuild everything?
It will not rebuild it, because right now it's not rebuilding it. We're just waiting for it to launch.
Okay.
If you make changes to it, if you don't save those changes, they will be lost. It's a temporary instance you get, and it will get cleaned up after a few minutes of inactivity, and then those changes will be lost forever. So you need to remember to take those with you. So you can see this takes a moment to actually spawn, and this depends a little bit on what time of day it is, how many other people are using it. But then what you get is a Jupyter notebook, and I will answer your question before we go on.
Who pays? I mean, if it's a Google Cloud or AWS or...
So right now we are very fortunate, and we have money from nice people called the Moore Foundation who pay our Google Cloud bill. And they also pay for people to work on this, because the actual cost of running this, so it probably costs about $40,000 per year in Google Cloud bill, but that's essentially for free if you would calculate how much in salary you have to pay the people who work on this, who mostly donate their time. Why is there a notebook now? Because there's a notebook in the original GitHub repository, and this is what the authors used to produce their figure. So maybe 30 seconds was a little bit ambitious, but we can now run this. So I potentially understand nothing about this code. I'm just executing cell after cell. And down here, we will make figure 1 from the paper. And if you go back, you can check that this is indeed the picture minus the nice annotations. And what's even better is if you spend a little bit of time now reading the code, you can figure out how to change the question. So they ask, how many large metal cylinders are there in the image? And it says 2. And I think you have to know that this guy is not metal. Because if I look at this quickly, then I go, that's 3 is the correct answer. But so we can now change the question. So yeah, I just change it a little bit. If you spend a little bit of time looking at this, then you should be able to figure out how to do this. So now it says 1 because there's only one large rubber cylinder in this picture. And I would say this, now if you want to talk about reproducible computational science, is how it should be. If I was actually seriously interested in machine learning and visual question answering, I would read the paper and I would have lots and lots of questions which can only be answered by actually running the code that they use to produce their paper. And step 1 in trying to run it, or even like change it to do my own research, is getting it to run. And if this takes 4 or 5 days, and I'm not even sure I will succeed, that's like a huge investment. And if it takes a few minutes, that's much, much better.
To take a bit of a counterpoint, I wonder if this sort of counts as full reproducibility of this particular project. Because it uses machine learning, it was presumably trained on some big data set that may or may not be available. So I guess what's happening here is that it's using the coefficients that resulted from the training that are saved somewhere. Yep. So it's really only the second stage of the project that is reproduced.
Yes. So they give instructions on. So okay. I'll for the video rephrase and repeat, hopefully truthfully, your question. The question is this really a full reproduction, or is it only part of it? Because it involves some big neural networks that have been trained on potentially large data sets, and all we have here is the coefficients or the weights, and we've used them. And I would say yes, that's true. They do give instructions on how to retrain the network from scratch, and I think it's some It's not Coco, but it's some fairly well-known public data set. They also tell you how many days of GPU time you need to do this. Yeah, that's the caveat. You need to have the money or the time or the patience to do it. They do give you instructions, so I would say you can at least hope that following the instructions will work, or it will be very clear that when they don't work, you can email them and say, look, your instruction, you said they will work, it's fairly mechanical to follow them, so it's clear that it's your problem to fix them, it's not my job. Because that's my experience often if you're trying to reproduce other people's software, you spend a lot of time discussing back and forth whose fault it is that it doesn't work. No, I wrote perfect instructions, it's your problem that you can't follow them, and you go like, no, I followed them perfectly. Your instructions don't work, and you know, at the end of the day you find out it's because you're using OS X 10.12.7 instead of 10. You know, whatever nonsense the problem is. Okay. So another title for this afternoon, or reproducible computational science, is running other people's code. And depending on who you ask, they will tell you running other people's code is either fun or very hard work or whatever. And this is a little picture from XKCD about trying to figure out which version of Python is installed where on your Mac. And so, you know, this is obviously for entertainment, but I recognize a lot of the boxes on this, so it's not completely made up. So there's several different approaches you could take to making, so the fundamental problem I think with running other people's code is that it depends heavily on the environment in which it was executed and reproducing this environment in which you should be running it. And there's several approaches to how you could fix this problem that it's really difficult to recreate these environments. You could take the approach that a lot of IT departments and big companies take. They just lock your laptop. There's a certain set of software installed in certain versions. Your laptop is locked, and if they're semi-competent, there's nothing you can do about that. And then that's very easy, because everybody in the company has exactly the same laptop with exactly the same software. And if I write something, I can send it to you, and it will run. The problem with that is that if you want to use any remotely modern software, then you have to phone up the IT department, and they will tell you, oh yeah, we'll check it, and then in 6 months' time they will install it, and you will like, yeah, now we need like version X plus 5, and you know, you wait another half year. So it's not a particularly good approach. There's also what I call the Wild West approach, which is more what I experienced in research, where basically anybody does whatever they want to do. You know, you're at the frontier, you're using the latest and greatest tools. The problem with this is that now I get an email telling me that Bash as terminal has completely like outlived its life, and we should all be using like future Bash version 7.9 or, you know, some other obscure software I've never heard of, and I should be switching to that anyway because it's much more productive than what I'm using. And I'm like, well, no way am I screwing up my laptop by installing crazy software that you kids use these days. And also, this is also not, you know, it works very well if you're all at the frontier, but if there's some people who like the more safe life in the city, then it's hard. So there's also then what a lot of people do is the kitchen sink approach. So you just package everything into the environment, and I send you a 20 gigabyte virtual machine image and go like, there's everything you need, just download it and run it and you'll be fine. And that's true, you know, you've built like a whole universe clone that you ship to people. When I was looking for a picture of this, I found this. So this is I think an oil drilling or gas rig itself, a very big ship, on a ship that transports ships. And you can go further. You can find pictures of ships on ships that carry ships, on ships that carry ships that carry ships. And, you know, it's fantastic. So this is a little bit the kitchen sink approach. So what I think is a better approach is the IKEA manual approach. I send you a manual that is so easy to follow, like an IKEA manual. No, you laugh, because lots of people are like, yeah, nobody can follow the IKEA instructions. But if you think about it, all of us, people who have no talent whatsoever in carpentry, can build fairly sophisticated furniture with some amount of help, following IKEA instructions. And the advantage of the IKEA instruction is, even for the oil rig, it's much, much smaller than the oil rig itself. So this is then what I think we should be doing for reproducible science, and what also the tools behind mybinder.org do, is we use Docker files to describe the environment in which your code runs. Because a Docker file is just a text file of commands that should be executed in order. So there's one problem with this. Creating a good Docker file that is also doesn't like balloon into something fantastically large and continues to work takes a lot of experience. And as a scientist, even now as a software engineer, I really hate writing Docker files. It's like the least favorite thing in my life. And the experience you need to write a good one is quite high. It's quite difficult. So expecting 99% of the people in the world to learn that skill, I think, is completely unrealistic. Case in point, now if you want to install one Ubuntu package, less, it's like some super small command line utility, in principle I think you need to write at least these 6 lines in your Docker file. And I cannot remember them. I copy and paste them every time I need them. So expecting everybody here to even remember that they need to go and look up the correct 6 lines is completely unrealistic. So what do we do? Or how did that paper do it? Yeah, because that paper just worked. So what is their magic ingredient? And you can probably, if you're in the front rows, you can read this and you can go on GitHub and check. There's nothing suspicious in this repository. Well, does anybody see something they find suspicious? No? And you already know that I'm going to trick you, no?
Environment.yml.
But is this suspicious in a Python package? Okay, so somebody pointed out there's an environment.yaml file in this repository. So it turns out there's a tool called repo2docker, and it does exactly what the name suggests. It takes a repository and turns it into a Docker image. And it will look at your repository and try and figure out from the files that are highly likely to already be there what it is you would like to have installed in your environment. So it mimics what a human would do. Now, step 1, it clones the Git repository. And then it analyzes it, and it notices that there's an environment.yaml file. And if you're a Python enthusiast, you know that this is one of the common ways that in Python land, people specify the dependencies of their project. So we go and look for this file, and if we find it, we go like, aha, this is what the author must have meant. And we analyze it, and yeah?
Sorry, you didn't want to. Is that the same as requirements.txt or the equivalent?
It's the same but different. It's a short answer. I will, in a few slides, you will hopefully be happy with your answer. So then it runs the command that if you went to the appropriate documentation, what should I do with the environment.yaml? This is the command you would find. It installs all of this, and then it runs Jupyter Space Notebook, and that is the UI you get. And now you can hook all this up to a little web server that runs in the Google Cloud. You can find some nice people who give you lots of money to pay Google. And then you have a web interface where you just put in the URL of a Git repository, and all of this happens in the background while you're trying to fill the time in your talk while you're waiting. So repo2docker understands you, Bastian, in particular, but all of you. It looks for lots and lots of files that are, so if you're in Python land, you recognize requirements.txt as something people use, environment.yaml. If you are a Julia person, does anybody here use Julia? Excellent. So you probably know what require in all caps means. You can, if you want to, put a Docker file. So if you really know what you're doing or you really enjoy writing them, you can. Yeah, this is our ultimate escape hatch, because there are some things you can't do. We try and make 90% of what people do possible, and then for the other 10% we go like, well, this is tough. You're gonna have to do your own thing. There's a few things we had to invent ourselves because we couldn't find something. So apt.text, for example, is if you want to install Ubuntu packages. There doesn't seem to be a convention that we could follow, so we invented one. Similarly, if you use R, we couldn't really find a good way that the R community has standardized on. So we invented install.r, and you list your R packages there. If you are an R expert, we would love you to help run or contribute to repo to Docker, because most of us are good in Python, but we dabble in R and Julia and C++ and so on. So if people have opinions on how that should be handled, what repo to Docker should recognize, then please get in touch. Yeah, there's also more obscure things like post build. So if you want to run some special commands just at the last minute at the end, you can put them in there. But most of the time you don't need this. So the point is that highly likely your repository already contains one of these files. Yeah, and then we just take them, and as a user you don't have anything to worry about. Okay, so we will talk a little bit. So the whole point of the rest of the afternoon is to show you how to use repo to Docker to build environments in which you can run fantastic research project which counts bikes in Zurich based on open data from the city of Zurich. And the things we will go through is create a GitHub repository, talk a little bit about how to manage dependencies on your computer, and if you want to, with a tool like repo to Docker. Then talk a little bit about repo to Docker and or mybinder.org. So the problem here is I think repo to Docker is the right tool for researchers to actually use every day on their laptop or on their machine at home, because it doesn't involve you having to publicize your code anywhere. The problem is all of you will have to install Docker, and if you have a Windows machine, then it's very hard for me to even help you because I don't use Windows. All I know is that it's hard. So we can try it, but for today maybe you can use mybinder.org, which is essentially just a nice UI to repo to Docker. We'll have a break, and then I'll talk a little bit about options for storing your data and storing your code if you are interested in more long-term storage than just GitHub. And then one thing I'm really a big fan of is notebooks as extremely fancy scripts. So I'll talk a little bit about this towards the end, and then how to keep it all working. So how do you've invested all this time in building something that in principle you promise works at the click of one button. How do you make sure that this is true without having to constantly go and click the button yourself? And when people contribute or you change things in your project, how do you to keep that working? And how far we get in this, or which of these we skip, depends a little bit on what level you guys are at. If you're all like virtual environments, Conda, I did that like already 15 times, then we skip that. If that's something that's new to most of you, then I would recommend we spend some time on it, and then we see how far we get.